There's high production value, my videos like a movie. This is sliding subarray 2653, the beauty. Okay, given an integer array nums containing n integers, find the beauty of each subarray of size k. Okay, the beauty of the subarray is the xth smallest integer in the subarray if it is negative, or 0 if there are fewer than x negative integers. Return an integer array containing n minus k plus 1 integers, because there's n minus k plus 1 subarrays, which then denote the beauty of the subarrays in order from the first index in the array. A subarray is continuous, non-empty sequence of elements within an array. Okay, so, for this problem, what we're basically doing, right, in this example is, right, we look at this example, nums equals this, and we're going to look at each subarray of size 3. So let's first go ahead and write those down, right? So the subarrays of size 3 within this array are -1, -1, 3. And then there's the subarray -1, 3, -2. And then there's the subarray 3, -2, 3. Right? So there's 3 subarrays within this system, right? There's this first subarray of size 3, this next subarray of size 3, and this final subarray of size 3, right? So we're going to have to look at each individual subarray, right? I guess that's the idea. There's always tips and tricks where in the code you may not actually have to look at every subarray over and over again, right? But the idea is you're going to look at each subarray, and then you're going to find the kth smallest value, right? So we want to find the second smallest value in this array that's negative. This is -3, and I'm an idiot. I apologize, everybody. Right? So the kth smallest value in this thing that's negative, right? Because if there's fewer than x negative integers, we don't want to return a positive one. So in this array, there's the negative integers are -3 and -1, right? So the kth smallest one, for the x smallest one, the second smallest one is -1, right? And this one, we got negative. Sorry. The smallest is -3. The next smallest is -2. The next smallest is -1. So our smallest is -2. Here we got the smallest is -3. The next smallest is -2. So our smallest is -2. Right? So in this problem, right, the brute force solution would be to look at each subarray, look at all of its elements, and determine the x smallest one, right? So that's what I literally just did here, right? We looked at this. We found the negative ones. We looked at the second smallest one. We looked at this subarray. We looked at everything that was negative. The second smallest one. We look at this subarray. Looked at everything that was negative. We look at the smallest one. Right? So in terms of time, well, we would have to look at all n minus k plus 1 subarrays. So basically n subarrays, right? Proportional to n. And then we'd have to, for each one, we'd have to look at we'd have to look at all the subarrays of size k, right? So we have to look at all n subarrays, right? We'd have to look at all n subarrays, and there's k elements in each subarray, so we'd have to look at all k elements of all n subarrays, and we'd probably have to sort it in order to determine, the kth smallest one. So that'd be k log k to sort that subarray. So that's n times k log k time. Is that sufficient? Well, n is less than 10 to the 5, and k is less than or equal to n. So that's going to be 10 to the 5 times 10 to the 5 times 10 to the 5 log 10 to the 5, which is 5. So that's 5 times 10 to the 5 times 10 to the 5. So that's 5 times 10 to the 10. That's far going to exceed time limit exceeder, right? So if you think of that solution, it's good because it shows an interviewer or yourself or whoever's opinion you care about in terms of the quality of your solution. It shows them that you can at least derive a solution, right? But it's inefficient given these constraints. But it's a solution nonetheless. So to kind of figure out what the optimal solution is in this approach, it's all based on the constraints. And the constraint that matters is this one here, right? It's kind of weird. If you see a peculiar constraint when you're solving a problem, it's usually an indication that peculiar, right, that strange constraint is contributing to what the actual solution to the problem is, right? It almost serves as a hint in itself, right? If there's a weird constraint, like in this example, nums of I is so constrained in what it can be, right? It can only be from negative 50 to 50. Why is that? Well, that's because it actually leads to a much more efficient solution since nums of I is so small, okay? But let's not worry about that now. What we're going to instead do is let's code up the brute force solution and then see how we can integrate in this weird constraint to make the solution more efficient. Okay, so we're going to want to look at all n. We're going to look at all the subarrays, right? So I'm going to write a code here to say, okay, how do I look at all the subarrays here? Right, all the subarrays of size k. So if I print nums of I to k, I to I plus k, will this code give me, will nums of I to k equal the entire subarray here? Why did I do n? Oh, length of nums. Sorry, n is the length of nums. I apologize. For some reason, I consistently make that mistake. You guys want to see what a real nerd does? 2-liter Diet Coke, no ice, no cup, straight from the source. All right. So does this give us all the subarrays? Well, there's 1, -1, -3, -1, -3, -2, -3, -2, 3. So this code, at least, you know, it's one example. One example doesn't prove anything. But it's sufficient enough to me to suggest that this is the solution because I've had enough exposure, right, to these kind of problems that I know that if I can prove it to myself with one example, that's sufficient to show me, okay, this is how I can look at all subarrays, right? So what we would have to do in order to do this, right, is we'd have our res array equaling this. And then what we would have to do is we'd have to look at this subarray and find the kth smallest element. Right, so what we would do is we'd say nums, we'd say res append, we would sort this array. Right, now this is the, you know, bear with me here because we're doing the inefficient solution here, right? So I'd sort it, I'd look at this subarray, I'd sort it, I'd grab the x smallest number, and I'd say, well, if it's greater than 0, then we don't want to return the kth smallest number if it's positive, right? We only want to return the kth smallest integer if in the subarray if it's negative. So we'll get the subarray, we'll sort it so we can find the kth smallest one, and then if it's greater than 0, then we don't want to use it, so we'll just set it to 0. Okay. And at the end, we'll just return res. All right. So we'll see if this works. Non-type object. Oh, because when you sort something, it's actually a void, right? It does like an in place kind of dealio. So that's just me being dumb. I apologize, everybody. And then I don't know if I'll be able to subscript it. You know, how good our syntax here is and how clear it is doesn't really matter because this is going to go away, right? Because I'm just trying to show you that there is a brute force solution, but the brute force solution is suboptimal. Okay. All right, so we sort it. When we sort it, what is that going to do? Well, it's going to take 1, 1, -3. It's going to set it to, it should set it to -3, -1. The second smallest. So we should sort it in reverse, right? See, these things get messier and messier. Just bear with me because this doesn't really matter. I'm just trying to show you that this works. Oh my gosh. Okay. So we want the kth smallest. So I'm trying to think about how this works. So if I wanted the kth smallest, right? So the first list is going to give me -1, -3, -1, 1. I want the kth smallest. So say the kth is the second smallest. I would want the first and oh, so I want to do k x -1 here. Sorry. Never a bad idea to walk through what's going on in your code. Okay, so this works, right? Now when we submit this, I don't want to submit it because it's going to error out and I don't want to affect my, you know, because I haven't submitted at all for this problem yet. So I don't want to affect my my percent score or whatever. But right, this is going to be far too slow to pass the time. It's going to give us a time limit exceeded. Well, not whatever. Let's just do it. So when I submit this, I'm going to give a time limit exceeded, right? Because I'm trying to do xk log k operations. It's too slow. And that's because we're trying to look at the subarray each and every time we do this operation, right? So instead what we can do is, well, let's look at this constraint, right? We know that, I guess, nums of I, right? It can only be in between -50 and 50, okay? So I don't know if you're familiar with this idea of like bucket sorting, right? Instead of, we know that, it's so hard to articulate this point. We know that, you know, our numbers are only going to go between -50 and 50, right? So the range of numbers is in range -50 to 50, right? 51 because, you know, it stops one before the end, okay? So basically, you know, if the numbers only go in that range, right? When we look at a subarray, we could say, well, if we instead just kept a track of the frequency of each number, right? Okay? And we, for the first subarray, how am I going to, let's do this not through the code. Sorry, I apologize here. Let's think of this a different way, okay? If we use the frequency idea here, right? Okay. We're doing size 3 subarrays, right? So if we first populated some dict with 1 has frequency 1, -1 has frequency 1, -3 has frequency 1, right? This would be our first subarray, right? 1, -1, -3, right? This would be the frequency of each thing. So what we could instead do is we could figure out the kth smallest element by looking at everything from the range -50 to 50, right? So I look at -50 and I say, is -50 in here? No. Is -49 in here? No. Is -48, 47? Eventually I'll get to -3. I'll say, is -3 in here? Yes, it is. How many times? Once. So now I know that -3 is the smallest element. So now I'm looking, now I know x equals 1. And then I look at -1 and I say, is -1 in here? And I say, yes. So we have x equals 2. We find a -3. Now x equals 1. We find a -1 and x equals 0. So that must mean that our smallest element is -1. Oh, I'm articulating this terribly. Okay. Then when we look at our next subarray, it's this one. -1, -3, -2. Right? Well, that means since I'm dropping off the only difference between the previous subarray and the current subarray is that I'm getting rid of a 1 and I'm adding a -2. So I'm removing one of the 1s and I'm adding a -2. So that's a constant operation that I did there, right? I just removed 1 from the previous subarray because that one's now away, and I add 1 from the new subarray, right? So that would mean, maybe we should do it, right? So to get this new subarray, all I have to do is take the previous subarray, kind of a running sum. The -1 becomes a 0 because I subtract that out from the previous thing, and now I'm adding in a -2, right? And then the same thing with the next one. When I have the final subarray, all that happens is, what am I getting rid of? A -1? Wait, the 1 stays. This becomes 0. Oh my gosh. All I'm getting rid of is this -1. So this -1 becomes 0, and I'm adding in a 3. So -3 is still 1. And I'm adding in, the -2 is still 1, and I'm adding in a 3, right? So now I can do a constant operation. And then what I can do to find out what the smallest are is, right, is since I know, basically what happens is since I have the frequency of each element and I can find the frequency in constant time because I just remove one from the frequency for the element I'm removing and add one to the frequency for the element that I'm adding, I can just go through the whole range from -50 to 50, right? And I can say, okay, if -50 is in here, then that's the smallest, so I remove that. If -49 is in there, I remove that. If -48 is in there, I remove that until I get X to be 0. So until I get X elements, until I find X elements, if I go in order, the X element that I find is the X smallest one, right? But since I'm only going, since nums of I, right, is trapped between -50 and 50, I don't need to check all the numbers, all the integers that can possibly exist. I only need to check these numbers. So I say if -50 is in here, then that's the smallest one. If it's not, then it's not the smallest one, and I keep going, right? So I go through the whole range. I'll set XX to X, and in this frequency array, which we will find, I'll say, well, if, I'll just say XX minus equal the frequency of this num, right? And if it's 0, then it's not in there. If it is, then it is. If XX is less than or equal to 0, that means that we found the number, right? Because now we've every time we find a number, the frequency of it, we remove it from X, right? If I find 10 50s in the array, I remove 10 from X, right? Because X is the smallest number, right? So the 10th smallest numbers are 50. And then if I keep going and then eventually I find there's a 30, a -30, then I remove the number of 30s from XX because that'll fill up the space, right? Because when I can recreate this array, right? When I look at this by doing what? I say, okay, -3, there's one -3. And then the next number I look at is -2. There's 0, -2, so I do nothing. There's 1, -1. Right? And then I look for 0. There's no 0. I look for 1. There is a 1. Right? And that's how I can recreate this array. Just by going through the whole range. Right here, I can go -50, there isn't 1. -49, -48, -47, -46, -5, -4, -3. Oh, there's a -3 in here. There's a -2 in here. There's a -1 in here. 0, 1, 2, 3, 4, all the way to 50. And from that, I can recreate this array in order. So basically, I get a bucket, right? I get a frequency of everything that exists within the range. And then I start at the bottom of the range and go all the way to the top of the range and collect the numbers, right? So I can linearly sort this thing, okay? And I only have to go from -50 to 50. So that's constant time, right? Regardless of the size of the array, since nums is constrained from -50 to 50, I only have to check from -50 to 50 at each operation. Right, so I say if XX is less than or equal to 0, then I say, okay, this is the number where, this is the X smallest number in the array. So I'd say res append this number. And I could put a break because you don't need to keep checking, but, well, it's going to keep appending. So yeah, we have to put a break. So we just break here. So this is pretty ugly code, but it's fine. Okay. So then how do I add to the frequency? So before we start, we're going to say for I in range k-1, we'll say f of nums at I plus equal 1. Okay. So what we'll do is when we start, we'll add in the newest element. So we'll say f at, so if I is here, we want to add in I plus k minus 1, because I plus k would be 3, minus 1 is 2. So f of nums at I plus k minus 1 plus equal 1. And at the end, before you do the next one, right, because when you're going to do these first three. So I start with the frequency array looking like this. Then I add in the -3. But when I go to the next one, I want to remove this one before I go to the next iteration. So before I go to the next iteration, I'm going to say f of nums of I minus equal 1. So I remove the current number. Okay. Okay. And then we'll go ahead and submit that. Not my best solution, but, you know, this is one of those problems where you probably need to learn a little bit about What's the problem with this one? So apparently I don't know what I'm doing. All right. For this array, we want to find, for size 2, the first smallest. Okay. So we look at -3 and 1. The first smallest is -3. Then we look at 1 and 2. The first smallest should be 0 because there is no, right? When we're looking at 1 and 2, it's still saying -3. So 1 and 2, when we look at 1 and 2, we're looking at 2. We should have because this is not indented. Forgot to indent some stuff. Cool. Okay, so what's the runtime? What's the space? Okay. For time, we have to look at all n. We have to look at all n subarrays. This is a constant operation. Constant operation. We have to do 100 operations here, right? But that doesn't have to do anything with the size of n. So this is constant with respect to, the inputs. Constant operation, constant operation. So this is big O of n time, where n is the length of nums. N is the length of n. Okay, and then for space, well, we have to create n space for res, right? In order to return res, we have to create an array of size n. So it's n space, but it's constant extra space, right? Because this frequency array can only have values from 0 to 50. So constant space, constant extra space, O of n space to hold res. All right, guys. We'll learn about bucket sort. That's going to help you a lot with this problem. Non-comparison type sorts.